Okay, thank you. So it's kind of that's continuation, but I recall something from my first talk. But let me start. There was a question by Tom.co. Your question, yes, about what metric Milnor and Thurston used. Yeah, I looked at this. I mean, we don't use it at all. Our approach is pretty different, but I looked at this, and it's indeed the Milnor metric, and this is possible because what is going on there? The map assign key points pairwise different on the complex plane, another p points, but to each such p points there is a Riemann surface which is plane without these points. Okay, so when maps different points, it kind of there is a Milnor distance between corresponding Riemann surfaces. First surface is first plane without this point, second. Okay, so it makes sense to talk about contraction in the Milnor distance. And again, so the map. I mean, it's not single value, it's more complicated, many valued map. But anyway, roughly speaking, it maps p points, where p is the period of critical point. P points, and p points means not just p points, it means Riemann surface, which is the plane without these p points, which are pairwise different, to another p points. And what does it mean, contraction in the quadratic distance, in the Milnor distance? You have two pairs of p points. It corresponds the one pair of the p points. It corresponds to pair of Riemann surface. There is a quasi-conformal distance, Milnor distance between surface, and then map F maps it to another pair of p points, so another pair of Riemann surface, and the question is whether it decreases strictly decreases this Milnor distance, and they prove that it is, but at the end they use Milnor theorem, extremal, so that there is one and only one extremal map. Of course, it is not available at all in our local situation, so that proof completely breaks down. So let me remind very briefly what is the setup that we consider. It's local. So we have this map of finite set into itself, which is called a marked map. And inside of this finite set, there is subset, which is kind of, I mean, in applications, these are critical points, but in fact, G extends to locally injective holomorphic map precisely at the complement of P0, P minus P0. So this kind of critical points, they can be, I mean, the map is even not extends as holomorphic in general. We don't assume it. But then we consider the vector of kind of critical values, just images of these points. In the neighborhood of these points, we already have a holomorphic map. Okay, and there are two possibilities: whether we start with a critical point and it hits after some iterate another critical point, or maybe itself, but in general another, and another complementary possibility that this one that we start with a critical point, and it comes back to some point of the same orbit, which is not critical. So it's kind of periodic situation. So there are two subsets of indices. And then we have a local holomorphic deformation of marked map. Okay. But again, the main point is that this local holomorphic deformation is parameterized by the points in the neighborhood of this critical value vector, okay, in C nu. So this W plays a double role here. On the one hand, it is in the phase space. On the other hand, this vector, which is near this, parameterizes the map. Okay, so okay, so that's.
Would you remind us what C1 bar is the vector of all critical values?
Well, they can be equal, but it doesn't matter. But we consider it as a vector in C nu. Oh, it moves. Okay, so here are examples. So much. Just one critical kind of point, one this image, which defines G capital. Okay, each point near in the complex plane near this point defines by definition this holomorphic deformation. In this case, this is just explicit formula, additive. Okay. And another possibility is this multiplicative form. Yet another, but it should be proved. I will talk about this later, I hope, that if G is rational map, then it can be naturally included in holomorphic deformation. Not all rational maps nearby, but rational maps that preserve multiplicities at the critical points. So locally preserve the number of different critical points. Okay, then it will be holomorphic deformation. Okay. And then naturally defined map from this neighborhood of critical value vector into the space of the same dimension, which just follows the critical relation. Okay, we start with, in the first group of indices, we start with critical value now and hit a critical point. Okay, which is precisely critical point. And again, just a name in general. With this index when double J is equal to f of C is equal to C1J, okay? Then this is 0. And this is the periodic situation. Again, this is precisely 0 at C1J in the second group of indices. And the definition of transversality when the linear part of this nonlinear map, this is nonlinear map from, say, if nu is 1, just a holomorphic map from C to C, where 0 with 0 at C1, 1, okay, the critical value. And it is, we call that there is transversality if the derivative of this map, linear part, is locally inverted. Is invertible, not locally inverted. It's just matrix. It's just linear map, so it's invertible. Okay. And if additionally, invertible means that the determinant is not zero. But if we additionally assume that this weighted determinant is positive, then you call it positive transversality. Okay, and then the transfer operator is defined along the orbit. Okay, so we consider for each holomorphic motion, which is just a holomorphic family of injection of this finite set, holomorphic family of injections, which start with identity, of course. We define the lift of this holomorphic motion, which is, this is the definition. So it is local inverse image of this map of the given holomorphic motion h lambda from next point of the orbit to the previous point. But the map changes. It is defined by the holomorphic motion of the critical values. So it is twists. It is twisted from from the market map to something nearby. Okay, every time. And this is the precise map we consider. Okay, so this is the definition. And in the case of additive family, this quadratic family, this is precisely Milnor-Thurston map written in holomorphic motions. But now the lift always exists locally because by monodromy theorem, for example, because locally it is always invertible, this map, so you can always do this. But it is still a nonlinear action. You take one holomorphic motion to another. And the linear transfer operator in this case is defined by linearization of this. So we take a speed of a given holomorphic motion and speed of the lift, okay? This is vector of dimension g of p. This is the same dimension. So this is a linear operator. Clearly it is linear because we take derivative, okay? Now some results which are not difficult to prove. First result, without any additional conditions, that transversality precisely is equivalent that one is not in the spectrum of this transfer operator. And moreover, if one is in the spectrum, so that it means that this determinant is zero, so there is some non-trivial kernel. So the dimension of the kernel is precisely equal to the dimension of the eigenspace of one. Okay, and the similar for real deformations. If you want to prove a monotonicity of entropy, then we need to use this. Okay. Now, one moment. Okay, that's precisely was missed page. Should I now go to share screen?
Yeah, share screen.
26. Share. It works. I mean, if you.
Yes, also 26.
Or maybe 27. No, that should be 26. So this is 26. Yeah. You see it, yeah? Yeah. Okay. So now the definition of the main definition. I mean, you see, there is no chance that the transversality or monotonicity would work always in this local setting, of course. So you need definitely some condition. And this is the condition. So we say that this holomorphic deformation has a lifting property if any holomorphic motion of this finite set can be lifted infinitely many times. So time after time. Okay, you start with first holomorphic motion, okay, h of lambda, then you consider its lift, which is h1 lambda, then you consider lift of lift, and so on. Each time you can do this, but possibly on a smaller disk. So with over a smaller disk of lambda. So we say that there is a lifting property if there is a non-trivial disk when all these lifts exist and uniformly bounded. Okay, this is the definition. And then it is clear, it should be clear that the lifting property already implies that there is no eigenvalue with modulus bigger than 1, just because if such eigenvalue exists, then you consider locally holomorphic motion with the speed at the eigenvector corresponding to this eigenvalue. Then if you then the speed of the lift is lambda square, okay, by this vector, if lambda is eigenvalue. So then speeds tend to infinity when you consider infinitely many lifts. Which is impossible because you have this condition that all lifts are uniformly bound, so all derivatives in lambda are uniformly bound. Okay, and then by the same reason, any lambda on the unit circle cannot have non-trivial Jordan cell because iterates of the Jordan cell are infinite. Okay. This is just a single page. Okay, now I should come back. No. So then the main theorem says that assuming the lifting property, everything is fine. What does it mean? It means that is not that there is an alternative. If one is not in the spectrum of A, then the transversality holds. That we already know, okay? Because the transversality holds if and only if one is not in the spectrum. So it's not very surprising. But what is surprising is that if one is in the spectrum, that you see, so what does it mean, transversality? It means that some surface or two surfaces intersect transversally, okay? But another possibility, if they touch each other. But this theorem says that it cannot happen. If they touch, they coincide locally, okay? That's it. So if one is in the spectrum, then there is a persistence of critical relation. That is, there exists a non-trivial manifold through this point, okay, which is the zero of this R, okay, on which the critical relation always holds, okay. So, for example, in dimension 2, by the uniqueness theorem, it would mean that this critical relation holds everywhere, which is definitely absurd, usually, okay. So somehow. Okay, now this is the main technical result. So now applications. So each time where some family has local lifting property, there is this transversality. And positive transversality, which means monotonicity of median sequence and monotonicity of entropy if the map is real. For example, so assume that market map is like this. So there is some kind of topological disk and another open domain U such that G is either covering map with a unique critical point or infinite cover. It could be several like this, okay, or petals, on which of them G is an infinite cover of this. So C0 is, in this case, a singular point, okay, and not critical. Then under this, then under the condition that the modulus of this annulus is big enough, okay, and this is the precise expression of this. What does it mean big enough? If you draw disk around C0 of radius diameter of this U, then it should be still inside of V. Then there is everything, okay? Then there is lifting property, which means that for each such family there is transversality and monotonicity of entropy if G is real. For example, it trivially holds for any, not only even, for any integer D. I mean, monotonicity of entropy, makes sense only for even, but this holds for any D. Okay, because as a U, you can take just big enough disk. Okay, if this initial disk is big enough, then for any WC, or W in this case, notation, in this big enough disk, it's pretty much will be well inside, and that's all we need. Okay, so then this famous result of monotonicity for quadratic family follows from this trivial actually. This is another example. Assume, for example, that you have a holomorphic family of polynomial-like maps with unique critical point, okay? And assume that the range is fixed, okay? And it is parameterized by the critical value for any point in the range. So any point in the range can be a critical value, okay, which defines the map, like for Z square plus C, okay? That's it. So for, but it's so if for each such C, the preimage of fixed domain is just inside, that's it. Then there is a lifting property. But yeah. Okay. This is a multiplicative version of this. There was this famous problem. Assume that there is a map like this, or family of maps like this, whether the entropy changes monotonically, and there were counterexamples, okay, of such families, okay? So in general, it doesn't hold, but I mean, what you have a single map, then you multiply it by a parameter, and you have family of maps like BZ, BX by 1 minus X, okay? And then the question is whether assume that G is, I don't know, convex or something like this. What?
So what is this drawing? What is the idea that there's a tension field?
No. Okay, so assume we have a marked map, okay, which is map of either it can be a map of an interval into itself, or maybe may be a map of half line, okay, like x exponent minus something like that, okay. And you consider any such G more or less. I mean, not any, but you consider such G, and then you build this multiplicative family, okay? And the question is whether the entropy changes monotonically, okay? There were counterexamples in 80s, I think by Anna Zdunik, for example. If I okay, so in general, it is not true, but we give sufficient conditions when for such family the lifting property holds, and then which imply monotonicity of entropy in such world. For example, these are of course a quadratic, which and then for example G of Z can be like this or can be like this with infinitely many critical points, by the way. But in this examples, the range is the whole C. But one can construct example when the range is not the whole C, punctured bounded disk. So it's quite.
Would you say what is the precise relation with monotonicity of the entropy? What is the statement? What is the
every time you have lifting property, then there is positive transversality, and then there is the monotonicity of Niedian sequence. Then there is monotonicity of okay. But the main condition we imposed for this to hold is that this map G from D to V has at most two singular values. At 0, single values could be critical values. At 0 and at C1, which is this C1. Okay. And then that's it. For example, for this sine Z square or sine Z. So what is this? I mean, they are well, I mean, all critical points map to one by sine. Okay, so this is the only critical value. Okay. Okay. Now the lifting property holds for rational maps. So all results about transversality. I mean, about this finite orbit. Okay, so if critical point is either periodic or pre-periodic, then this is a particular case of, again, this approach, because we prove that any rational map can be, there is a natural, this deformation, which I describe later, hopefully today. And then we prove the lifting property, which is essentially here is the Thurston algorithm. Okay. Then it holds for Arnold's map and some Lorentz maps, for example, linear Lorentz map, and also with this singularity. Maybe I did not pay attention. So this is another example, interesting. So where 0 is not a critical point, but singular point. Okay, that corresponds to this. To this picture. To this picture. Okay. So the critical point here is flat. It's 0, where L is any real number. Okay, so again, everything is okay. Okay, now our main initial motivation was this family. Unfortunately, we could not prove the lifting property for all combinatorics. But we prove it for many combinatorics. The main condition is if you consider 0 to be a periodic point and assume that the number of iterates of this periodic orbit where the map is decreasing is uniformly bounded, and consider all such L and C, then for there is some L star depending only on this number, so that for L bigger than L star, there is this the lifting property and the transversality. But in general, it's still open, whether monotonicity holds. Well, and some other results. Maybe I don't have time. Okay. So this was about finite steps of critical relations for, for critically finite set one case one. But there is another part which was actually motivated by a question by Remenka, who asked me 4 years ago when I was visiting, part of my sabbatical, was visiting one stream, Sebastian one stream, and suddenly Remenka asked me how to calculate. There was apparently some discussion where he was involved on the internet about how to calculate the number of real small copies of the Mandelbrot set. So copies which on the real line, intersect the real line. So, and it's not difficult to answer, assuming that all primitive components cusp look at the same direction, okay? Which means that once periodic orbit is born on the real line, it cannot disappear when you go to -2, okay? Of course, it was known, it was proved by Doherty and Hubbard in RSA notes, but the proof is global. And turned out that the same approach, our approach, worked in this case too, local approach. So let me not say a lot about this. So, but definitions are the same. The only thing is that first of all, there is just one critical value, so nu is 1, okay? And there is an orbit of this critical value. Again, critical value is not critical value because there is no critical point here. It is just marked point, okay? And there is an orbit of this, but in application, this is critical value. So, and the local deformation is parameterized by this parameter near this critical value C1 initial. And there is an orbit by the marked map G, but which is infinite. And this orbit by the condition, there is a definition of local Lorentz information, which is the same, but with infinite set. And by the condition, this orbit converges to a periodic orbit, okay? Where still the marked map stands to holomorphic locally. So this periodic orbit is either attracting by hyperbolic, so its multiplier is like this, but hyperbolic, not zero. Or it is parabolic, but non-degenerate. Okay? Non-degenerate means if it is parabolic with this multiplier, then this iterate, I mean, all these things between 0 and p, I mean, they are 0 always. So, and then non-degeneracy means that the first coefficient which can be non-zero is actually non-zero. Okay. For example, if the multiplier is just 1, it means that the second iterate. I mean, this is just non-zero. This one. Okay. Now, then there is this local Bayesian of attraction. In the hyperbolic case, this is just the whole neighborhood of this periodic orbit, and in parabolic case, this is petal. Okay, I mean this is this flower, low flower. If k is 1, this is just one petal. If k is say third root of 1, then this is the picture. And then the main theorem in this setting is the following. So assume that this holomorphic deformation of such marked map satisfies the lifting property, but this time it's not enough that only on the orbit. It should satisfy the lifting property of in the Bayesian, okay, in this local Bayesian. It can be as small as we want. Okay, together with this infinite orbit. And then everything is great. Again, the same alternative. So either there is a persistence of periodic points with the same multiplier, which is amazing. So either there is a persistence, so either multiplier was some k at parameter C1. So there is a periodic precisely with the same multiplier, or with multiplier 1 if it was 1, or there is a transversality in this sense. The derivative, if the periodic orbit was either attracting or parabolic with not 1, then this periodic orbit, of course, by the implicit function theorem, persists in a neighborhood. So the multiplier is a holomorphic function. So then this derivative of this multiplier at the parameter, at the initial parameter, is not 0. But if the multiplier was 1, then of course this function doesn't exist. But then this non-degeneracy condition holds. So it unfolds, I mean, in a non-degenerate manner. Okay, so the derivative with respect to parameter at C1 is that if both these conditions can be expressed as just one inequality. I just wrote it separately. And for example, this for the quadratic family, in the real case, primitive component corresponds to, I mean, cos correspond to this k is 1. For the quadratic family, it means that this is non-degenerate, which implies that all these small copies of the small primitive hyperbolic components are in the same direction. Okay. But good news are that the lifting property, even in this on this bigger set, holds for all these classes of maps that were before. So all these examples that were before fall in this theorem. And the corollary is that periodic orbits, once in these classes of maps, once appear on the real line, don't disappear. If we go in a positive direction, which positive direction mean increasing of entropy. So maybe we can break. break.
10 minutes.
Okay, so I left the best part to the end. Oops. I'll try to give some ideas. This main theorem in the not for the attraction and parabolic periodic setup, but for this first finite set. So this is the statement, okay? So this is G is marked map over of finite set, okay? G capital is holomorphic deformation, and there is a lifting property, and then the claim is that either one is not in the spectrum of A, and then there is transversality, which we know already, or one is in the spectrum, and then the solutions of this equation form a smooth non-trivial manifold near this point vector C1, okay, which is the zero, of course, of R. So this is the statement, and the proof. Some ideas of proofs should be somewhere. Oh, sketch. Okay, I need some definition. Holomorphic motion of this finite set over some disk is called asymptotically invariant of order M. Okay, if its lift, what is lift? It is a finite collection of holomorphic functions in lambda. Near zero for collection is over the point of the set G of P. So if its lift coincide with the initial holomorphic motion up to lambda to the power m. So if you expand this in the power series in lambda, then up to lambda to the m, this is the same, okay? This is just the definition. But it makes sense even for m as 1. What it means for m1? It means that the linear paths of the lift and the holomorphic motion and the holomorphic motion itself are the same. But that precisely means that one is in the spectrum of A. Okay? If you think about this, more precisely, one is in the spectrum of A, if and only if. So what it means, one if in the spectrum? It means that there is a fixed eigenvalue, a fixed eigenvector, which is not identical zero. So, but what it means, eigenvector? It means at each point of G of P, of this finite set, there is a vector. I mean, vector which is coordinate of this eigenvector corresponding to 1. Okay, so there is a field of vectors over this finite set. And then if it is fixed, but given such finitely many vectors at finitely many points, you can always include it in a local holomorphic motion just by linearity. So if at the point, if the vector at the point x is v of x, then you define x plus lambda v of x. And if lambda is small enough, and the set is finite, it defines some holomorphic motion. But this holomorphic motion is precisely asymptotically invariant of order 1, because when you consider lift, then the linear path does not change. precisely because 1 is in the spectrum. Okay, so asymptotically invariant of order 1 means just that 1 is in the spectrum. Okay, more precisely, 1 is in spectrum if and only if there is a non-degenerate holomorphic quotient, and more precisely, the speed of this holomorphic quotient corresponds precisely this eigenvector of this 1. Okay, and then. Well, this is the fact, but then the main technical part of the proof is the following lemma. Lemma says that this: suppose that there is a holomorphic motion h lambda, which is asymptotically invariant of order m. Okay, m is 1, 2, something like that. Okay, so some m. Then there is a non-degenerate holomorphic motion, another h lambda, over some smaller disk, which is asymptotically invariant of order m plus 1. Once there is, for example, once 1 is in the spectrum of the operator, so there is asymptotically invariant of order 1, then there is asymptotically invariant of order 2, 3, and so on, because you can pass from m to m plus 1, infinitely many times. Of course, reducing the domain of definition. Okay, and this is the connection of this asymptotically invariant for the m plus 1 to the asymptotically invariant for the m. They coincide up to m. And the idea of the proof is this. In fact, that is how to find this asymptotically invariant of the next order, m plus 1. You consider all lift sequence of all lifts of a given holomorphic motion, which is asymptotically invariant of order m. By the lifting property, they all exist over some non-trivial disk. Then you consider averages of such holomorphic, of such lifts, and they are uniformly bounded in a fixed disk by the lifting property. And then, hence, it has some limit point. Okay, and the claim is that any such limit point is asymptotically invariant of order m plus 1 already. So there is one more, in the Taylor expansion, in the power series expansion, that disappears for this limit of these averages. Okay. So and well, there is some proof of that's. But that's the main point. Here, consider averages and limit point, limit function. Now, about the proof of the theorem based on this. Let me, okay, first of all, if the lifted property calls that the spectrum is in the closed unit disk, we already know this.
Could you please remind what is the main theorem?
Yes, the main theorem, okay, maybe I'll say. So assume the lifting property, okay? Then there is an alternative. Either 1 is not in the spectrum, and then there is transversality. This is if and only if, in fact. Either 1 is in the spectrum, but then not only there is no transversality, but there is a non-trivial manifold with critical relations around this critical point, okay? So they cannot touch, they have to just be the same in a neighborhood. Okay, so and that's what we want to prove now. So assume that 1 is in the spectrum. Then we know that the dimension of this eigenspace corresponding to this eigenvalue 1 is equal to the dimension of the kernel of this function, which defines the transversality or not. Okay, so the kernel is non-trivial, but moreover the dimension is equal just. And now just let's consider it's the simplest case, Tsujii idea that mu is 1, just one-dimensional. So like quadratic, for example. Okay, then there is just one, and mu is 1, and assume for simplicity that 0, that the critical point is periodic. C0 is periodic. So then R of omega is just this one function where P goes from the critical value to the critical point, given function. Okay, so, and now we need to prove that if one is an eigenvalue, then this is identically zero in the neighborhood of C1, okay? So assume that it is not the case, assume that R is not identically zero, then it has some expansion, which starts with some M and with some A non-zero, okay? Because it's not identically zero. But we know because one we assume is in the spectrum and together with lemma, it implies that there are holomorphic motions of arbitrary asymptotically invariant order, okay? So now take a holomorphic motion of asymptotically invariant of order M, where M is this M, okay? We know we already have some M, finite M. So we know that exists asymptotic right, of order M, okay? Then just define this function, in this case, just mu is one. But then it is easy to recognize then, so asymptotically invariance of order one, of order M along the orbit, okay? But when you apply more and more this G capital, then it stays the same along the orbit. So when you come to the end, to the R, come back to C1, then you obtain the same asymptotical invariance. So the first non-zero possible term is lambda to the power M plus 1, which is absurd because if omega of lambda is this function, okay, then it corresponds to eigenvalue 1. So it means that omega of lambda is equal to C1 plus V lambda, where V is first coordinate of the eigenvector corresponding to eigenvalue 1, so it is not 0. And then this is contradiction. On the one hand, it has to be like this. On the other hand, it is like this, where this is non-zero. So this is a contradiction, okay? Which proves?
So here, at the end, you use the property of existence of asymptotic invariant for some particular order.
Particular order, we assume that R is not zero, and R is not identically zero. Then there is some first non-zero term of some order, okay? And we take this one. We don't know if M is 1, then we are lucky, but it can be some other. That's why we need a split differential of all order, just in case.
You have asymptotically invariant holomorphic motions of any order. Is it possible to construct some formal, in some sense?
Some just infinite expansion.
Yes, some holomorphic motion, maybe formally, or formal holomorphic motion invariant of infinite order.
Well, there is this procedure. No, it's kind of transcendental. You have infinitely many lifts, then you consider its averages, then you pass to a limit, and you get the next order. Then you have to do the same. Consider infinitely many lifts of this function, take averages, and pass to a limit. So it's
But then the disks where these things hold, or is more.
they shrink, of course. Yeah. But for any given M, it's some disk. But if M tends to infinity, they shrink. Okay, now that's for finite set. for the this parabolic attraction and parabolic setting, the proof, the main theorem looks the same, but you have problems everywhere. For example, the first technical problem that you face is the following. Here, if you have finitely many points and vector field at finitely many points, then you can always include it in holomorphic motion locally, just by linearity, okay? But if you have infinitely many points and vector field, then it is not the case. If you know that this vector field is not Yoder, but Lipschitz, then it's okay. You can do it by linearity. But in general, not. And here, in the first part, we proved the following. Assuming that this transversality fails, okay, it means some equality at the end of this sequence. And then we proved that under this equality, you can extend this field to one holomorphic motion, okay? And in the case of attracting periodic orbit, it in fact we found after all that was a lemma in a paper by Avila, Lubitsch, Demela. But in the case of parabolic periodic orbit, which is much more involved and technical, that's much more difficult to prove, and that's the main case we wanted to consider, parabolic, if multiply 1, for example. So this is the first technical problem we faced, and there are other problems, but I will not talk about them. Let me switch to rational dynamics, because I promised to talk about proofs there as well. Okay. So, okay, now I talk about transversality in spaces of rational functions. We gave elementary proof of what kind of what was known before. Okay, so the first thing to fix is in what space of functions, rational functions, we are. So, I mean, if you consider all rational functions of field degree D, then it can be considered as an open subset of this projective space. Okay. For example, if it is quadratic, then 3 coefficients here, 3 here, and up to multiplication by the same. So if this is in the projective space of dimension 5. Okay, but it's too big for us because if, for example, given map F has multiple critical points, then in this space, this critical point splits into several ones. There is no way to be some holomorphic deformation in this case. So we consider subspace. Abstractly, it goes like this. So given collection of positive integers, we say that a rational function f of degree d is in this space corresponding to this vector. If f has precisely nu, which is the number of this in this lift, number of multiplicities in this lift, when f has precisely nu distinct critical points of the corresponding multiplicities from this list. Okay. For example, if this vector is just all ones, then that means that 2d minus 2 non-degenerate critical points. Okay, so this is definition. Now, the following fundamental fact that I think was known also. For each vector, this set, this is a subset in Rd. So this is an embedded in the set of this open set in projective space, submanifold of dimension nu plus 3. Okay, but that's not very crucial. But what is important that the vector of critical values form a partial holomorphic local coordinate system. Okay, so it cannot be the whole coordinate system because if you take F and precompose it by Möbius transformation, then the set of critical values stay the same. Okay. So, and this Möbius transformation gives 3 more coordinates, okay, together with the list of critical values. Okay, so this is the, so now we have, given F, we have this submanifold of functions which preserve critical points with the same multiplicities as F, okay? And I think maybe first explicit similar statement appeared in Roman-Kolubich paper about spaces of entire functions with finitely many singular values, okay? Also about rational functions, it appears in my paper, but it was known maybe also to Yeremenko, but all this proof used the measurable Riemann theorem with dependence on parameters. Okay, so something, and the idea, this is just Thurston algorithm. And it goes back to Tech-Müller. So we give elementary short proof. You just, I mean, calculus 1 would be enough probably to understand this proof. Okay, but it is based on an idea by Duadzi in Sentenac in some paper about note about polynomials. Okay, so this is this is the first thing to define the space of maps. So we have now given F, we have this space of map. Okay, now what next? So we have this F, and we consider G in a small neighborhood of F, and by the definition, we have all critical points of F move holomorphically with G, okay, by the definition actually of this space. The distant and the bound from G. Okay, now given a collection of four numbers, integers, non-negative. So I, J, M, and N, where I, J are supposed to be indices of the critical points. So there are critical points, C1, C2, C nu, okay? And M, N are supposed to be iterates. So, but such that not both of them are 0. We say that this collection is a candidate critical relation. That's it. I mean, whatever you have the collection, we declare that this is a candidate for critical relation. But it is realized by F if naturally this holds, okay, for this collection. So it can happen that I is equal to J, but then of course, it always holds if M is equal to N, but it is non-trivial if there is a critical relation if M is bigger than N. So after M iterated, come back, N can be 0. come back to it to some other critical point or to another point of the orbit. And then for each such realized critical relation, we associate this quadratic differential, this one, which appeared already, I think, where it is assumed that if m or n is 0, then the corresponding path is 0, so it disappears. Well, it formally doesn't exist, but by the convention, it is just 0. And then we prove the following theorem. Assume that the critical orbit avoids infinity. Critical orbits. It's not a problem by change of by Möbius transformation to maybe because critical orbits is countable. Okay, now so let F be a finite set of critical relations which are realized by F. Okay, now we know what that's. I mean finite. I mean n actually critical relations like this. And they satisfy a non-cyclic condition. So there is no cycle of such indexes. By the definition, cycle is like this. Okay, where iterates are always 1. Okay, so 2 critical points go to 1. Then there is another critical point go to the same. Okay. It can happen, but if but in the collection of F that we choose, we just if this happens, we just cross it out. Okay, don't include. Okay, now what is the goal? Is the goal to prove that if there is this finite collection of of critical relations which are realized by F, then the rank of this map is maximal, is n. Okay, that would mean transversality.
So you care about in the cyclic relation, you care only about the case n equal to 1?
Yes, yeah, only. Oh, yeah. Okay, and then, but the theorem says that if the Jacobian of this map has rank less than n, that is, there is no transversality, then, first of all, there is, what does it mean less than n? It means that, okay, then there is a collection of n numbers, not all of them zeros, such that in our collection F, there is, these numbers are supposed to be, maybe it makes sense to first consider on this linear combination, okay, of this quadratic differential. And so, I mean, here these numbers are not all 0, of course, otherwise it doesn't make sense to consider such that in this combination, there is at least one k such that m non-zero, which is such that m k and nk are not 1, 1. Because if for all ak non-zero they were 1, 1, then this each such quadratic differential would be 0 just because we start with critical values, okay, there in the difference. So it means that this condition guarantees that here there are rational functions which are not 0, okay? And the theorem says that this linear combination, non-trivial linear combination of these quadratic differentials, which are not all zeros, is a fixed point of this this Ruelle-Thurston transfer operator corresponding to function f. And then it is known that, in this case, if you look at this, then if it is fixed point, then you conclude that Q has to be integrable quadratic differential on the whole plane. But then it is known that other than it cannot exist if it is not zero, other than in what the case, okay? And that's essentially, proves transversality. So what's the task now? The task now is to choose a collection F with no cycle condition, and such that this linear combination would contain a kind of pole which is not killed by other members. Then it cannot be zero. Okay, and then it proves transversality. But that's another task, how to choose this collection F. There is some algorithm in the paper how to choose this F, but that's not related to this transfer operator. Okay, I didn't tell you the proof, but another proof. A statement similar to this, I think, we wrote, should be in somewhere in Adam Epstein's papers. I don't know precisely where. And also it was proved. It follows from my paper, which was known, which appeared before, because it can use the following explicit relation between the transfer operator and the derivative with respect to the critical values in some space of maps. Okay, but all these proofs are more complicated, definitely. And we give a simple proof. First of all, based on this lemma, which I stated already. This lemma. So this is pullback operator acting on Beltrami coefficients. And then for each realized critical relation, we have this quadratic differential. And then the lemma says that there is some family, holomorphic family of rational maps through map F, such that on each this quadratic differential, on the one hand, this is just expressed by integral f. On the other hand, it turns to be a derivative with respect to parameter t of this difference. Okay, and the proof uses Thurston pullback argument, which is this theory of quasi-conformal mapping. Let me just say a few words about this. How to construct this family Ft? It is like this. So take any mu, okay, but mu, for some technical reason, because we need to find derivative with respect to parameter of quasi-conformal families. So for that technical reason, we need a normalization at infinity. The map is holomorphic with this normalization. But then mu has to not only for mu, but also for pullback. Then we have to choose mu, which is zero in the neighborhood of infinity and in the neighborhood of f of infinity. And then it's well known that if then for each such mu is in L infinity, then if t is small, then t mu is in the open unit ball of, obviously, of L infinity. Then for each such dilatation, there is quasi-conformal map with this normalization of infinity, unique. And this quasi-conformal map corresponding of this dilatation, which this is pulled back. Okay, and then it's also well known that one should consider then that this map is rational because that was my attempt to write in a few words introduction to the quasi-conformal maps. But what is important is this, that why it is rational, why it is holomorphic. This is quasi-conformal. This is quasi-conformal. Ft should be downstairs. Because geometrically it is clear. So psi t takes pullback field of ellipses to circles. So inverse takes circles to ellipses. But the definition of pullback, derivative of f, takes this ellipse to another ellipse with dilatation mu. Okay? And then by the definition of Pt, we come back to a circle. So after all, Ft maps fields of circles into fields of circles, which means it is holomorphic in Z. That is rational. Okay, and then there is some proof. Some proof. And this is formula for the derivative of family of holomorphic maps with this normalization, with this C mu dilatation at 0. Okay, there is some simple, few lines proof, which after all uses the fact that at the end, Fm iterate of Ci coincides with Fn iterate of Cj. So it's not just a formal critical relation, it is just realized by it. Okay, then the proof of theorem 2. So assume that the rank of this map, of this map, which is defined by this coordinates, is less than n. Then there is a non-trivial linear combination which has all partial derivative with respect to coordinate of the corresponding space to be 0 at f. But then it means that if we have any holomorphic family through f, the derivative with respect to t at 0 has to be 0 because by the chain rule, okay? And for the linear combination, then we have this linear combination. By lemma, we have this equality for each critical relation, but then we consider linear combination, and we know that this is 0. And after all, if you look at the beginning, then you get that the Q is the linear combination, that this integral vanishes for every mu, because you started just with some mu under this condition, which implies that Q is a fixed point. Okay, I would like to stop.
Are there any questions? If not, let's thank Genadi again.